Welcome back to our Algebra 2 series. Today we are up to section 5.2 where we will be looking at exponential and logarithmic relationships. Just to review, here is the generic form of an exponential function. So if a is some positive real number constant other than 1, because that would be boring, we have an exponential function with base a. F of x is equal to a to the x. A is the base and x would be the exponent. We also discussed logarithmic functions as well. So if y equals a to the x is an exponential function, y equals log base a of x would be the logarithmic function. And as we discussed before, a logarithmic function is the inverse of an exponential function. And as you can see, these two formulas are the same, except the x and y variables have been swapped. They are inverses of each other. So let's start with this example. 2 to the x equals 8. We know we can rewrite this as x equals log base 2 of 8. And the way I like to think about it is that we have a base of 2 to the x power equals 8. So for another example, we have 10 to the 3 equals 1,000. We can rewrite this as 3 equals log base 10 of 1,000. We've done no real math here. We've just rewritten the same equation a different way. You can just as easily go back the other way and turn a logarithmic equation into an exponential equation. So let's take this example. Y equals log base 3 of 5. We can rewrite this as 3 to the y equals 5. Here we have log base 2 of x equals negative 3. We can rewrite this as 2 to the negative 3 equals x. And since we have a negative exponent, we can move that to the denominator. 1 over 2 cubed equals x, or 1 over 8 equals x. In this case, we were able to solve for x fairly easily. We're going to use this new notation of f to the minus 1 of x. This just means that it is the inverse of f of x. So let's take this example. F of x is equal to 3x plus 1. What is the inverse of this function? First, let's rewrite this as y equals 3x plus 1, and then swap x and y in that equation. Next, we just need to solve for y, and that gives us y equals x minus 1 over 3. So we can say the inverse of f of x is x minus 1 over 3. So if we put these next to each other, and let's start with a real number, f of 3. If we put 3 into the original equation, we would get 10. 3 times 3 is 9, plus 1 is 10. Let's take that answer and put it into the inverse function. What would be the result of the inverse function with the input being 10? Well, it's 3. We ended up right where we started. This is further proof that this is the true inverse of the original function. Another way of saying this is that the inverse function can use the original function as an input, and you'd end up with whatever the input is, x. The opposite of that is also true. You could take the inverse function as your input for the original function, and your result would still be x. So we know we have these two relationships. A function and its inverse will always have this output. So what happens when we do this with an exponential function? Well, we know that the inverse of that function would be the logarithmic function. So if we take a to the log base a of x, we will simply end up with x. That's assuming we keep the same base. Likewise, if we take log base a of a to the x power, we still end up with x because we're using the same base. This may look weird and a little complicated, but it's important to understand that the logarithmic and exponential functions are inverses of each other. Let's jump over to the whiteboard and do some examples. So we're going to start with a pretty basic exponential expression. Y to the negative 1 equals 4. And what I want to do is convert this into a logarithmic expression that means the same thing. So let's put the word log over here. We know we're going to have a log here. And over here in the exponential side, the base is y. So we're going to have log base y at least. We know that much. And the resultant over here is going to be what we're taking the logarithm of. So it's log base y of 4 equals whatever the exponent is over here, -1. Likewise, we could write something like -2 equals log base x of 7, and I want to convert this to an exponential equation. This is our base, so we know that this is going to be the base. The result becomes the exponent, and this becomes the resultant. So we end up with x to the -2 equals 7. X to the -2 equals 7. I think about this little arcing path. X to the -2 equals 7 would be the exponential way of writing this logarithmic expression. Let's try writing a slightly different equation. We're going to put the variable over here and say that x is equal to log base 27 of 3. So let's rewrite this as an exponential equation. So we would write this as the base of 27 to the x power equals what we're taking the logarithm of, 3. We're going to do one more example that looks like this, but we're actually going to solve this one. We're going to say that 1/2 is equal to log base x of 4. So again, we're going to rewrite this as an exponential function. It would be the base x to the 1/2 power equals 4. So now we've got x to a 1/2 power. How are we going to get this to a normal x? Well, we can remember our good old algebra days here, and we could square both sides. So I think I can squeeze this in here. We're going to have x to the 1/2, and we'll square it. That's going to equal to 4 squared. So if we have this, x to the 1/2 squared is just x, right? So we're going to multiply, we'll have 2 over 2. We have just x. And x equals 4 squared, which equals 16. Let's clean this off and look at some of those inverse functions. So this is going to look a little weird, but we're going to take 4 to the power of log base 4 of 3. And what does this equal? So we have an exponential equation, 4 to something, but the something is a logarithmic function. And 4 is the base of this exponential expression, and 4 is the base of this logarithmic expression. So going back to our inverses and f of x and f minus 1 of x, this just ends up being 3. And we're actually just going to rewrite those expressions out here so we have them. That a to the log base a of x equals x, which is what we just did here. And the other way around would be log base a of a to the x equals x. So kind of going back to the other way, if we wrote log base 10 of 10 to, let's say, 3.2. So we're taking the log of something that has a base, but the something is also an exponent. So the resultant of this, we could look at this expression here. When we take the log of something that has the same base to any power, the answer is that power. So the answer just ends up being 3.2. That's it for today. It's a pretty short section, but we'll see you next time.